Hi everyone. Did you know that ChatGPT and AI are not actually the same thing? Well, this should be pretty obvious, but nowadays when you hear most people in business talking about AI, what they're really talking about, or most of the time what they're talking about is ChatGPT or some other variant of a generative pre-trained transformer, which is the base technology that ChatGPT is built upon. Similarly, a lot of people seem to think that this is kind of like the pinnacle that we've reached of AI, and that any other type of simpler model that preceded the invention, that preceded all the developments in GPT is kind of outdated and useless at this point. And that's something I really disagree with, and I think that it's important to remember that what model you use is going to depend a lot on the problem you're trying to solve and what data you have. And that's kind of what I want to talk about in this video. I want to take a step back and look at XGBoost and talk about how specifically it can be optimized on GPU to really excel on certain tasks in terms of efficiency and accuracy. So yeah, this is all the different fields of AI, not all of them, but what I'm going to talk about is predictive analytics. This left corner over here, bottom left, whereas something like ChatGPT would fall under natural language generation. So yeah, I want to talk about XGBoost. XGBoost is it's an ensemble tree-based machine learning model. It's supervised and you can use it for classification or regression tasks. It was really popular in the mid 2010s when people were using it to win a lot of Kaggle competitions. But then once all this started happening in NLP and people kind of seem to have discarded these and forgot about them, but I still think they're really useful, and um, especially if you're trying to train it in parallel on a GPU. So first I want to talk a bit about some of the background about how these models work. Um, so I think we all kind of know what a tree is, or a decision tree. A decision tree is you have a set of your training data and you're basically trying to make sequential decisions to split up your data in a way that where your splits are going to increase your information gain or reduce the impurity. So, and then you're going to reach a point where at the bottom, at the last level of your tree, your data is going to be separated in an optimal way. We all use decision trees like logically in our head all the time, but we don't really think about it. One common example that you'll hear if you study this at school is if you want to go play tennis, like let's say you're thinking about going to go play tennis today. So what's the decision tree that you'd go through in your head? It's first is like, well, do I have anything else going on today? Do I have to go to work? If yes, then you're not going to go play tennis because you have to go do this other thing. But if no, it's going to take you to like, is the weather nice out? And then like, are the tennis courts open? Or do I have anyone to play with? And it's a bunch of these different like split binary decisions. And eventually you're going to have classification for like how you decide whether or not you want to go play tennis. Um, but no matter how well you split your data, there's always going to be an error between, especially when you're training, there's always going to be a difference between what you're predicting and what the actual value is. And the fancy term for that is loss. So if you're doing a regression task, this is kind of what a good visualization of what loss would look like. Every time there's a squared error, there's a difference between like this green line, which is what you're trying to fit, and the gray line, which is the best possible way to separate your data. One more intuitive way to think about this is if you're like shooting a bow and arrow at a target, you want to hit the bullseye, which is your target, but you're not going to hit it first. You're going to probably miss, and the distance between where your arrow hit and the target, that's what we refer to as loss. And you're trying to minimize that loss to get as close as possible to your target. Um, and one key point about machine learning is that if you can define a loss function mathematically, that's really powerful. So for regression tasks, a loss function would be something like mean squared error. Like in this line, squared error would be the sum of all the squared distances between the red dots and your line. And the lower the squared error, the better. You're trying to minimize that loss. But for a classification task, your loss function would be something like cross entropy. And when we talk about gradient, gradient is you hear that a lot about you hear that a lot in machine learning too. Gradient descent obviously is very fundamental, but gradient is the term that we use to describe the partial derivative of the loss function with respect to every predictive parameter. And if you know anything about derivatives in calculus, you know that it tells you the rate of change of a function. And since we have our loss defined as a function, if we know what the gradient of that function is, we know what direction we need to go, um, what direction we need to update our feature values so to increase the rate of change in our original function by the most. So we're trying to decrease our loss function. We want to minimize this distance to the bullseye by the most possible. And the way you do that mathematically is by finding the negative of the gradient, like the steepest path down, which is going to decrease your loss function by the most. So that's kind of a good way to think about this. And in gradient boosting, that's exactly what we're trying to accomplish. XGBoost stands for extreme gradient boosting. And the idea is that if we can come up with a way to boost our gradient to like get a faster way to decrease our loss function. And the way that's implemented in XGBoost is you get a series of trees rather than just one single decision tree. You get a bunch of decision trees sequentially, and every next tree, rather than trying to fit it on your original data set, you're trying to fit it to reduce the loss that the previous tree made. So every time you're iteratively trying to improve on the performance of the prior tree, and I know that sounds a little bit perhaps kind of weird at first, especially if you're not familiar with this concept. Um, but if you've ever watched Squid Game, you can think about like the glass bridge game, where the first person that goes, they're gonna have a huge mistake. Like they don't really know where to go, and then every next person is gonna adjust their approach based on the mistakes that the previous person made. In this case specifically, the loss would be pretty dramatic, like, but you get the point. So what that would look like in a boosting scenario here is that you have your data and you learn, and then the feedback would be the loss that your first model made. And every time you're trying to iteratively improve upon that. So XGBoost is just this, but where every individual learner is a decision tree. Mathematically, the tree we're adding at every iteration is supposed to minimize the loss of the previous tree while also adding a regularization term to make sure that you're not overly complicating things and adding computational overhead. And then the final prediction you get is just going to be the weighted average of all your different tree predictions. And in theory, this should work a lot better than just having like a single decision tree. This is the alternative to tree bagging models. If you've ever heard of random forest, what a random forest is you're just having like a bunch of trees that you're training in parallel, and you take the average prediction generated by all these trees. So that's all cool, but the key point is that XGBoost is super powerful because this iterative process can be done in parallel, and you can easily run it on GPU using CUDA and NVIDIA Rapids. So I want to talk about a little bit like how that works mathematically because I think that's really cool. And then I'm going to show a practical example of how you can do this yourself in Python if you actually want to try this at home. So yeah, so remember that um, every possible time we want to add a new tree to our boosting scenario, the idea is you're trying to minimize the loss from the previous tree. Well, this calculation can actually be done in parallel. Um, and the reason why is that when you create your single tree, like how do you do this? You basically try to go through each feature and figure out how to make the splits based on what's going to give you the most information gain. And how that's done is you um, you can, oh wait, that's on the next slide. Here we go. So for each node in your tree that you're trying to add, what you're going to do is you're going to sort your features, the instances by the feature value, and then use a linear scan to decide what's the best split that you can get along that feature. And you take what the best split is among all the features. And what's happening is that since you're doing a linear scan of all the different features, each feature you can assign it to a different thread block on your GPU, which means that this whole splitting process can be done in parallel. More specifically, XGBoost does this using something called histogram construction. I'm not going to get too into how that works specifically, but when you're trying to figure out like how to split your tree, the statistics that you need the gradient, which is what we talked about, which is the first derivative of the loss function with respect to every feature. And then you also need the second derivative or the Hessian. And then you use those statistics to figure out like how to calculate how you're going to build your next tree. Well, as it turns out, the gradient and the Hessian are additive, so the way you do that is um, basically you're gonna split the different feature values into separate bins and calculate the first and second order derivatives for each bin, and then add them up to get your the full statistics that you need to make the splits. And by splitting the calculations onto different GPU threads, you can use the GPU memory layout known as column storage to compute the information gain in parallel using shared memory. And rather than doing this iteratively, like you go to each node one by one, you calculate what the best split would be for each feature, you can just pass this in as a whole parallel block at once onto the GPU. So if you think about a tree, rather than visiting every node individually, you go like level by level and do this calculation. And then you pick what split is going to give you the most gain using something like multi-reduce or multi-scan, which I'm not going to talk about now, but if you want to get a little visualization of what this looks like, that this is the idea. So once you figure out what your best split is, you use that to update your tree and you iterate on to the next tree. But I hope that gave a little bit of a sense of how this works and why it's so powerful. But I know that this is just a lot of theory, so it's more useful to actually see like what the performance boost would be if you did this in practice on a training set. So that's kind of what I'm going to try to do now. Um, let's go on to this. Um, let's move on to the tutorial portion of this video. So what I have right here is a notebook. I don't have a GPU on my laptop, but I do on this server. So what we have is an Intel i9 CPU versus an RTX A6000 GPU. And I'm going to explain like how you train an XGBoost model on CPU and then how you do it on GPU, and then I'm going to compare like the performance of the two just to give you a sense of what's going on. So the first thing you want to do, first make sure that you actually have a GPU on your computer. I know that sounds dumb, but a lot of people like overlook that. And once you're sure of that, you want to create a Conda environment where you can actually import the QML libraries that you need to interact with your GPU via CUDA, which is the NVIDIA library. So the way that you do this, it's pretty easy, but I just want to show you guys. You go to docs.rapids.ai/install. You put in all the different combinations of what like machine you're working on, like what you want to use, and it'll give you this conda command right here. So you copy that and you create your environment. Once you have your environment created, you connect to it. Like make sure you're actually working in that environment, which is what I'm doing right here, Rapids 24.08. Once you're in that environment, you can pip install other packages that you want to use. So one that you definitely need is XGBoost, and some other ones I have here, like sklearn. So first do all of that, and that should give you like the necessary environment that you need to actually do this. Now, I'm not going to use a real data set for this example because I just want to show the performance. Like I want to generate a random data set of random numbers, 100,000 rows by 100 columns. The XGBoost performance gain that you're going to see is going to become a lot more apparent when you're working on a large data set. Um, all right, now let's get into the interesting part. What I'm going to do here is something called a random grid search. What that is, first, basically you're iterating through different hyperparameter combinations for your model and trying to figure out which combination of hyperparameters gives you the best model when you're training on the data. So a hyperparameter in those are kind of things that you tune, like when you're tuning a guitar or something, you're trying to get the best like combination of um, features that's going to give you the best model. There's plenty, but the ones I'm going to use for simplicity's sake, max depth is how many levels there's going to be to the trees that you're building when you're going iteratively. And the min child weight is the weight that you're putting on the leaf nodes in your tree. So there's obviously like a lot of different values you can use for these, and rather than training them one by one, what you can do is try every different combination, train a model using each hyperparameter combination and see which one does the best. So that's something that's used a lot in practice, and it's good to know. That's kind of like how you find what model is going to work best. And once you have your grid of parameters that you want to like try out, you can build this function. Feel free to copy what I did here. But this is the key difference. When you want to train XGBoost on CPU, you're going to use the XGB regressor function um, and pass in the parameters. And then you just fit on X-train and Y-train. Kind of standard. But when you're doing this on GPU, your one hyperparameter that you need to set is the device to CUDA. That's how XGBoost is going to know that you're trying to train this on GPU. And another key thing that you need to do, this is probably the most important part of this video, you can't just pass like a regular array or NumPy array into a GPU training model for XGBoost. That's because of what I talked about earlier when I was going on about the theory, where we're trying to calculate the splits for the features in parallel, going level by level for the tree. And in order to do that, you need a specific data structure that's going to optimize the GPU threads, calculate each feature on its own thread. And in order to do that, um, fortunately, XGBoost does that for you with something called a D matrix, but just don't forget to make a D matrix of your training data. So like if you try to pass X-train and Y-train onto your XGBoost model on GPU, that wouldn't work. It needs to be as a D matrix. So that's what I've done here that I'm showing. And once you have your D matrix, the train, you train it, but you don't use the XGBoost regressor, the XGB regressor, which I did for CPU. You don't do this. That's not going to work either. You just need to call it xgb.train with your params and the D matrix as an argument. So it's really, like I said, it's really simple. They do a lot of the hard work for you, but just don't forget to, go through the necessary steps and understand like the theory about why this works so well. So now that I've got all that set up, I'm going to go through this random grid search and fit to my like randomly generated data set on CPU first. I'm going to run that and probably going to have to pause this video and get back to you when it's done. Alright, so this finally just finished running. Took about 4.5 minutes. Now I'm going to run the same thing, but with GPU. First, it's always good to check if your GPU has memory available, which looks like I do. Not fully, but shouldn't be a problem. And let's see how long it takes to run the same exact code, but using GPU training. Alright, so 9.7 seconds. Let's try to. Okay, so looks like we got a speed up of about 27 times, What you could also do if you want to check, it's also I should mention that this is like GPU on this server isn't even fully free, and it's only on one RTX A6000. Another big benefit of a model like XGBoost is that you can actually run it on a cluster of distributed GPUs pretty easily, and that you can even use out-of-core computing when you're running your XGBoost training, which means if you have a data set that's massive and it won't fit on your RAM, you can still it uses sharding to actually handle that, so you can still train on like a really large data set. So overall, extremely powerful, especially for industry applications. Another thing that you could do if you want is compare the performance of the two, just to like verify that one isn't working like very differently than the other, which they shouldn't. We're not going to get a good R squared here because we're just literally just training on random noise. It's not any real data. But yeah, as you can see, looks like the GPU actually worked a little better, but it shouldn't really be much of a difference. This is the key point right here, this speed up. So yeah, that was the whole point of this video, just to show the intuition behind models like XGBoost. I know that LLMs and transformers are super popular and trendy right now, but that doesn't mean that any older, kind of simpler approach can't be just as powerful, if not more powerful. Don't let the hype distract you from that. And that's a big thing that we believe in at Seas when we're building our pricing models for cars. So I guess the key takeaway is that it's not the size of the model that matters, it's how you use it. So yeah, thanks for watching.